Hi, I am Idil Özdamar from Koç University, and today I will present our paper entitled as Step Change in Friction under Electrovibration. We investigated how step change in friction induced by electrovibration affects our tactile perception and finger contact mechanics. This study is supported by the Scientific and Technological Research Council of Turkey. Electrovibration makes it possible to modify surface friction on a touchscreen. This is achieved by applying a voltage signal to the conductive layer of a touchscreen. This technology has applications in online shopping, education, teletouch, games and entertainment, user interfaces, data visualization, and aids for blind and visually impaired. However, our knowledge on the tactile perception and contact mechanics underlying electrovibration is highly limited. To investigate tactile perception and contact mechanics for a step change in friction, a custom-made experimental setup was developed. The major components of these setups are arm and hand support, a capacitive touchscreen whose horizontal and vertical movements are controlled by two stages, and a high frame rate and speed camera for real-time finger imaging. In this study, rising and falling friction are investigated. The rising friction is obtained by turning on the voltage at the middle of the traveling distance, whereas the falling friction case, the voltage started with on condition and turned off at the middle. Our perception results show that rising friction was perceived significantly stronger than falling friction. The difference between intensity scores of rising friction and falling friction was always positive. Moreover, sliding velocity was positively correlated with the intensity scores, while normal force had negative correlation. The coefficient of friction as a function of displacement under rising and falling friction are displayed in the figures. We observe that rising friction have higher contrast than falling friction, and contrast values are decreased as normal force increase. Our results on change in finger contact area show that rising friction resulted in further decrease in normalized contact area, while the opposite was true for falling friction. The contrast was higher for rising friction, and the contrast difference between rising and falling friction reduced as normal force increased. This result is not surprising, since electroadation is known to be more effective at lower normal forces. We observed that rising and falling friction had opposing effects on finger pad deformations. The regions of the finger pad that had been compressed at the onset of the movement were further compressed for rising friction and partially relaxed for falling friction. As a result, compressive and tensile strains were formed. Again, the contrast in strain values was higher under rising friction, and they converged to similar level as normal force was increased. All in all, our results reveal that the contact mechanics of rising friction is significantly different than that of falling friction, possibly due to the viscoelastic nature of the finger pad skin, and this difference affects our tactile perception. For more detailed information, please read our paper.